Hello, everyone. My name is Giancarlo. I am a postdoc here at UDAP, working with Andre and, Cole Monahan, James Orson from the Alaska Center here in Seattle, and James Sullivan from the Alaska Center in Juneau. And today I will be talking about the somatic growth variability and I will be talking about somatic growth variability and start space assessment models. This is a new, I would say, a new field in the stock assessment models. I will be showing my work that we have been doing during the last few months. This presentation is going to be about 35, 40 minutes, so it's not going to be long. You have questions, you can leave the questions in the chat box, and Emily is going to help me with that. Okay, just for an introduction, I will start talking about somatic growth. As we know, somatic growth is a change in length or weight in a fish population. Just to give a very quick background about somatic growth, what we have different somatic growth variability in fish populations. I am going to present this figure. I like it a lot because in this figure we can see the main three phases during the lifespan of a fish. In a stage 1 or phase 1, all the energy is directed to somatic growth, to the increase in biomass of the fish. And this first phase, we can see it here. And during this phase, there is no energy for sexual maturation. In a stage 2 or phase 2, the energy is going to be directed to somatic growth, but also to sexual maturation. And we can see this energy here. So the fish is going to increase in biomass still, but a percentage of that energy is going to be invested in sexual maturation. In the last stage, or stage 3, use a few percentage or a very small percentage of the energy is going to be directed to somatic growth, and most of the energy is going to be directed to reproduction. And this is the last stage that we can see here. So this is why during the first stages of the fish, we are going to see a very fast somatic growth increase, a very somatic growth rate. And then during the last stage, we are going to see that the fish is not going to increase in biomass, and all the energy is going to be invested in reproduction. So this curve, just to say, a last thing about this, this curve is very well known among fish populations. I mean, we are going to see a very, very similar pattern for different fish species. From this pattern, there are many equations that people or fishery scientists that try to fit to this data. Now, also somatic growth is an important contributor to biomass variability. This is also a well-known paper published a few years ago. And in this paper, we can see that there are two main contributors to the biomass variability in a fish population. It could be recruitment, or it could be somatic growth variability. And before this, most of the people, I would say, saw that the main contributor was recruitment, driving changes in biomass, expanding biomass in the population. However, for some fish species, we can see that the contribution of somatic growth variability is as important as the contribution of recruitment variability. We can see here in this plot, we can see, for example, for the peacock, we are going to see a very similar contribution of somatic growth variability and recruitment variability in the spawning biomass variability of the population. Now, there are, what we observe in the field is that there is going to be somatic growth variability in space or in time. And this variability is caused by different factors. In this figure, I am going to show you 3 factors, but there could be many more. For example, in figure A, we are going to see the effects of temperature, which is a very well-known environmental variable studied. And what temperature does to somatic growth is that it increases the somatic growth rate. What we can see here is that the blue line is showing the growth curve in a cool environment. So the temperature is low here in this blue line. And we are going to see here is that the fish increase in biomass or in length at a very slow rate. However, in a warm environment, we are going to see that this increase is going to be much faster. So the temperature normally increases the growth rate of the fish population. Of course, this is just a general pattern that we observe, but this is going to depend also on many factors such as food availability in the environment and other factors. But this is, let's say, like the general pattern that we observe. In figure B, we are going to observe the effects of the fishery. In this black line, we are going to see the growth pattern for a fish population without fishing mortality. So for this black line, there is going to be only natural mortality. But when the fishery is introduced in this equation, we are going to see that this pattern shown here by this gray line, and we are going to see that the fishery normally increases the growth rate of the fish population. And in this figure C, we are going to see the effects of the prey type or the food quality. And here I am going to show two different preys. For example, for the prey blue, let's say, the growth rate is going to be a little bit slower compared to the prey red, which is going to be a fish here. So depending on the prey quality, we are going to see a slower growth rate or a faster growth rate. So there are still many factors that affect the somatic growth variability, and I am showing here just three very clear examples of those. Okay, we know that there is somatic growth variability in the environment of the fish population, and that somatic growth variability should be accounted in stock assessment models. Now I will start talking about the stock assessment model. And especially I will be talking about static space assessment models, which is the assessment model that I am working on for this project. So static space assessment models, the main feature of those models is that they allow the separation and estimation of both observation and process errors. I am summarizing here in just one slide the main point of static space assessment models. What we can see here is that we are going to have two equations first. We are going to have the observation equation and the process equation. The X letter here represents the unobserved state. This is a state that happens in the population. Let's say, for example, the population abundance. And this Y letter represents the data that we have. The T represents time, and this theta represents a set of parameters. So in static space assessment models, we are going to separate the observation error and the process error. The observation error is related to the data and what we get from the model. This expected value, for example, can be calculated from a function of what happens in the population. This is why I represent here this X, and also a set of parameters that account for this observation error. For the process error or for the process equation, we are going to be studying what happens in the population. So for this case, this expected value can be calculated by is a function of what happens in the population in a previous time step, but also a set of parameters. So when we study static space assessment model, we are going to separate these two processes into equations or into parts. So this is a very simple way how we can represent this. And also something important that I have to mention here is that we can have some fixed effects, which is represented here by this theta letter, which is the vector of all unknown model parameters. And these parameters are normally treated as fixed effects. But also we can incorporate random effects, and these random effects can be predicted on the unobserved state, on the axis. So for this case, we can, for example, predict random effects on population abundance, or we can predict random effects on natural mortality, everything that happens in the population. Okay, this was a very quick summary of style space models. And there are several reasons why we should use them. First, there is evidence that they can handle structural breaks and time-varying parameters. They can handle also missing observations and can be used to do forecasting. This is a very important point because the style space assessment models keep the error structure in the data that we have, and that error structure can be projected a few years in the future. We can model complex and nonlinear relationships, and we can predict, or we can get less retrospective bias. There are already several papers that show these few points that I am showing here. Okay, that's about the style space assessment models in general. And now I will start talking about a very specific type of style space model, which is called the Woods-Hull assessment model 1. This style space assessment model is a fully stat space age structure model. We can incorporate data, we can use data such as catch information, indices of abundance, age compositions, empirical weighted age, and also we can include environmental covariates. This model, models the separability of total catch and proportions at age, as well as the annual F and selectivity. So we have that separation. And we can predict random effects on selectivity parameters, natural mortality, abundance at age, and catchability parameters. It is written in TMB, in Template Model Builder, and R, so it's very user-friendly. It's very easy to understand how to use it. And there is an R package, if you are interested in this model. There is an R package, and there is already a lot of help, a lot of sources how we can implement a style space model in this platform. However, there are some limitations. This is a quite new platform. I would say this started to be developed just a few years ago, I think 5 or 6 years ago. So this is still a new platform. So therefore, there are some limitations. First, there is a lack of best practices for random effects use. When I say this, is that it's not very clear how we should predict the random effects in what way, and what is the meaning of that. What I have seen so far is that we normally predict random effects in on many parameters, and we always try to get the best model, but there is still a lack of what is the meaning of that. So in what cases we should use this type of random effects, in what cases we should use a different type of random effects. So there is a lack of best practices to do that. Growth cannot be modeled internally. Selectivity at age options, there are selectivity at age options, but there is no selectivity at length. This model is single sex, there is no spatial component, no aging error. And yeah, this is just a few limitations that we have. As I said, most of these limitations is because this is still a quite new model and a quite new platform. And also, I will say like maybe this growth functionality that I show here is because this model was developed in the East Coast. So there was no a need or an important need to model growth in that part. However, if we want to use this platform in the West Coast or in the Alaska region, the length information and growth variability is going to be very important here. So for that reason, we wanted to expand, or we wanted to work on this platform to do an expansion and be able to incorporate length information and also model growth internally. Yep, I don't know, Emily, there are questions. I will take a break here.
I don't have any at the moment, but if anybody has any, please feel free to drop them. If not, Giancarlo, do you want to keep moving on and I'll stop if I see anything?
I will stop by seconds, 10 seconds. Okay, I will continue. Okay, this was just the introduction of my presentation. I have introduced the style space assessment models and the wood school assessment model, and also the somatic growth variability in fish populations. So now I will start talking about the growth modeling in style space model, specifically growth modeling in the one style space model.
Actually, Giancarlo, I do have one question. Yep. Emily Legestrand says, can some of the aging error in WAM, I'm assuming, be accounted for by alternative proportionate age distributions like the Dirichlet multinomial?
Sorry, can you repeat the question?
Sure. Can some of the aging error be accounted for by alternative proportionate age distributions like the Dirichlet multinomial?
That's a good question. I haven't thought about it. My guess is no, because the Dirichlet only deals with the different sample sizes and the autocorrelation among ages. So my guess is no, but I haven't explored that. Actually, aging error is a feature that is not implemented yet here. But yeah, that's a great question.
She says, thank you.
Okay, cool. Now I will start talking about the work that we have been doing during the last few months. And this is the one expansion. Now we have new features for this platform. We can incorporate new data inputs. For example, we can incorporate marginal length compositions and conditional HL length data. This conditional HL length data is used, I would say, like a lot for some stocks here in the West Coast and the Alaska region. And it's simply an H-length key. And this is a very important source of information for growth variability. So this is why it was very important for us to incorporate this new data input. And marginal length composition are very similar to the edge composition, which are marginal edge compositions. So it's the same concept. And as I said, these two data inputs are important sources of information to model growth internally in WAM. Now, when we model growth internally in WAM, I will be referring to two types of growth variability. When I say growth variability, I will be talking about changes in mean length age, but also it could be changes in mean weighted age, because growth variability can be studied in both ways. But something that we have to keep in mind is that changes in mean weighted age is going to be affected by changes in mean length age, but also changes in the condition factor. The condition factor is the A parameter of the length-weight relationship. It's a very popular length-weight relationship. So that variability can also affect these changes in mean weighted age. And the changes in mean weighted age is linked to the changes in mean weighted age through a length-weight relationship. That's why the changes or the variability in the condition factor is very important here. So this is just something to keep in mind here. If we are going to model changes in mean weighted age, we are really combining two sources of variability, the changes in mean weighted age, but also changes in the condition factor. This is maybe some basic population dynamics, but it's important to remember. Okay, this is a summary of the model growth modeling overview that we have now for WAM. We have different options to model growth internally, and I will be talking about these options in two sections. The first section will be changes in mean length age, which is going to be represented here by LAA, and changes in mean weighted age, which is going to be represented here by WAA. Okay, changes in mean letter age. We can use two options. We can use a parametric growth equation. Let's say we only have one option so far, which is the von Bertalanffy function, the very popular von Bertalanffy function. This is the parametric approach, I call it. And the second option that we have is predicting random effects on mean letter age. I will talk about this in a few minutes. So we have two options: a parametric approach and a no parametric approach. This second approach is what I call it the no parametric approach. Now, for the changes in mean weather age, we have three options. The first option is the classic option that is already implemented in WAM, which is using an empirical weather age information or matrix. And in this empirical weather age, there is growth information contained in this input. But the problem here is that this empirical weather age is assumed to be known perfectly. And we all know that this is not true. There is some error in this data. So that's something also to keep in mind here. So this is the first option, which is the classic option in WAM. The second option is predicting random effects on mean weather age. This is also a no parametric approach, similar to this approach for the changes in mean weather age. And the last option is using the changes in mean weather age and also a length relationship to model changes in mean weather age. So in this last option, it's going to use information from changes in mean weather age and also a length relationship to calculate or to model changes in mean weather age. That's why I put here two lines, because these two lines are linked here, but it's not linked here, because this option, this no parametric option, is not going to use this information. And now, using all of this, or using this mean weather age information, we calculate the spawning biomass and reference points. Now we have different sources of informative data to model changes in growth. For this option and for this option, for changes in mean weather age, we can use the observed mean weather age information, which is similar to the empirical weather age. However, this observed mean weather age is going to be used with error, and we are incorporated a likelihood function here. And also we have marginal length compositions and conditional agent length data. And these two sources of information are going to be important to model changes in mean weather age. So this is a diagram like summarizing all the options that we have so far. And now I will be talking about each specific option that we have. And in the first section, I am going to talk about changes in mean weather age. And as I said, the first option is a parametric equation. In this case, it's going to be the von Bertalanffy equation. This is quite popular. This equation uses three parameters. We have the asymptotic length, we have the mean length at age 1, and we have the growth rate. And just to let you know that the first age in WAM is age 1. Is age 1. So this is different from stock synthesis, for example, that uses the first age is age 0. So just to let you know that. And yeah, this is a quite popular equation. These two equations calculate the mean letter age at the start of the year, on January 1st, and then we can calculate the mean letter age at any fraction of the year using this second equation. Okay, this is quite clear, I think. And also, we can now predict random effects on these growth parameters. For example, this is just a very simple representation of this. We are going to have three main parameters here: the asymptotic length, the growth rate, and the mean letter age 1. And we can predict random effects, which is going to vary by year. This T represents here by time. It's better to say. I say time because it could change by year or by cohort. So we can here predict random effects, which is going to vary by year or by cohort, and they can be independent, or they can have some kind of temporal autocorrelation. So we have now these options. So, okay, that was about the parametric approach to model changes in mean lead age. And now this is the no parametric approach to model changes in mean lead age. This is what I call the LAA random effects. And for this case, the mean lead age is going to be treated as parameters. And we can predict random effects on these parameters. We are going to start using one vector. This vector is going to be the mean lead at ages. So it's going to be from age 1 to the plus group. And then we can predict random effects. We can be independent or can have some kind of autocorrelation. And these random effects can vary by year, by ages, by year or by ages or both. So we want to have here a full variance covariance matrix. Now, this is the no parametric approach. And now, with that information, with information of mean lead age, we can also calculate the age length transition matrix. And this transition matrix is important. I think I will explain it in the next slide. But this transition matrix is very important when we include length information in a stochastic model. And to calculate this transition matrix, we are going to need some extra parameter here, which is going to tell me about the variation of length at age, which is known as sigma or CVs in some cases. So with those parameters, we can calculate this transition matrix. And we are doing this in a similar way how stoch synthesis does it. Okay, and this transition matrix can be plotted in this way. Maybe it's not the best way to do it, but it's going to be helpful maybe here. So we are going to have different ages. And for each age, what we are going to do here is to split the abundance at the age across lengths. This is the main use of this transition matrix. For example, if we have 100 individuals here for age 1, we can split those 100 individuals among two length means. For example, 50 individuals for length mean 2, and 50 individuals for length mean 4 centimeters here, for example. And that's the main use of this transition matrix, is just to split the abundance at age across lengths. And this is a way to plot it. And of course, the sum of columns here is going to be 1 always. Okay, cool. Okay, there are questions so far. I will stop here a few seconds. This was about changes in mean lead age, and I will let you know if there are questions here. Okay. Okay, I hope that is clear enough. And I will continue to the next subsection, which is going to be about changes in mean weather age. And as I said, we can use a length-weight relationship here. This is the classic length-weight relationship. I call here the parameters omega-1 and omega-2, but some people call it A and B. It's the same. So we're going to have 2 parameters here. And also we can predict random effects on these parameters. And these random effects are similar to the random effects that I showed for the parametric equation for the growth parameters. So they can be by year or they can be by cohorts. And then using this relationship on also the transition matrix, we can predict the mean weather age internally. And this mean weather age can be and this mean weather age can be fed to the observed mean weather age that we can use, represented here by this symbol. So this is why we can now incorporate this observed mean weather age that I show in the diagram. And also, this is a different strategy. We can predict random effects on mean weather age. This is very similar to the random effects on mean weather age. So the structure is super similar. We are going to start with a vector of mean weather age, use a single vector. And then we can predict random effects on this vector. And these random effects can vary by year, by ages, or both. Okay, that was about changes in mean weather age. So that's all about. I just finished talking about the internal growth modeling. And now I will also let you know that there are a few more options for other parts of the model. For example, for selectivity, we only had selectivity at age functions. We had four options. We had age-specific, logistic, double logistic, and decreasing logistic. However, now we have new functions because since we have length information in the model, we thought that it would be good to add new functions, selectivity at length functions. So we have these four new options. We have a double normal, which is going to be by age. And we implemented this function because here in the West Coast and Alaska is very used. And this, the parameterization of this option is very similar how stock synthesis does it. And also we have three options to selectivity at length. We have a length logistic function. We have a length decreasing logistic, and we have the double normal also, but for by length. So in total now we have 8 options to model selectivity in one. And also we have the option to implement or to incorporate environmental covariates, and these environmental covariates can be linked to any parameter in the model. So previously, we only have options to link environmental covariates in recruitment, natural mortality, and catchability parameters. But now we can also implement environmental covariates and be linked to any growth parameters if we are using the parametric function, or also the mean level age or the no parametric approaches. Just to let you know here that the one separates the process and observation error for environmental covariates. And this is pretty cool because one treats the environmental covariates as observation. So this observation has some error in there. So the one estimates internally the process error and the observation error. I am not going to show all the questions because it was already well studied in previous presentations. So I am going to summarize only these in this simple equation. Environmental covariate can be linked to a state. When I say state here, it could be a parameter. In this way, it could be very simple, but also there are more complicated ways to do this, using polynomial functions, for example. And all those options are already available for the growth parameters and also for the no parametric approaches. So I just wanted to tell you this slide is just to tell you this, that these options are also available for the new parameters that we have now. Okay, I will stop again here and I will wait for questions if there are.
I don't see any in the chat box at the moment.
Okay. Okay, what I present now, I will present now is a few examples that we have implemented here just to test the new features that we have in one. And I will present 3 examples. For these examples, I use stock synthesis. Specifically, I use SS3Sim to simulate data. We use SS3Sim to simulate data, and that simulated data was then incorporated into one. And we did this because we needed some data to test the new features. And we didn't want to use one because we didn't know that one was really working with these new features. So that's why we use stock synthesis, because we know that stock synthesis is already working. So we use stock synthesis as the operating model. We simulate data, and the data was then incorporated into one, used to test the new features. So I am going to present 3 examples. In the first example, I will model growth variability in the operating model. In the second example, I will simulate a conditional HR length data and also a double normal selectivity function. And in the last example, I will model variability in the condition factor in the operating model. Now, for this first example, was about the growth variability. We simulated catch data only for one fishery. We simulated an index of abundance used for one survey. We simulated marginal length compositions for a fishery and for the survey. And we also simulated variability in the asymptotic length parameter. This is the asymptotic length parameter of the growth function using the PDO as the driver of changes. So we use the PDO and the asymptotic length change over years following the PDO trend. Now then, with that simulated data, we implemented 3 models in one. The first model is predicting random effects on the asymptotic length parameter. So this is using the parametric approach to model changes in mean letter age. And these random effects are independent, and they're gonna be year specific. In a second model, we implemented the no parametric approach to model changes in mean letter age. And the random effects here were independent, and these random effects change by year and by ages. And in the last model, we include an environmental covariate, environmental variable, which was the same, the PDO. And this environmental covariate was linked to the asymptotic length. Okay, I am not going to show all the results that we got from these different models. I am just going to show, maybe this is not the best. I need to increase the size of this plot, but this is maybe the most important plot that I wanted to show you. And this is showing the variability in mean letter age. This LAA means mean letter age, and the x-axis is time. And we have here 4 different models. Here's this purple line is the operating model. So that means that this is the result from the stock synthesis. This is the real variability. This red line is the model in one that included the environmental covariate. This, let's say, green model is that a model that implemented the no parametric approach to model changes in mean letter age. And this blue model is that model that implemented the parametric approach and predicted random effects on asymptotic length. So generally, what one can see here is that for younger ages, the pattern over time is very similar for all models, especially when we have more data, especially when we have data for the fishery, which is very important for the model. That's why that for age 5, for age 6, 7, especially is 5, 6, and 7, we have a very clear variability for the no parametric approach, which is the green line. So that means that the model needs a good source of information to model changes in mean letter age for the no parametric approach. And also I say this because for older ages, that's for example, for age 16, age 17, age 16, this no parametric approach is not predicting any variability in mean letter age. And this is because we don't have a lot of data for older ages. So the model doesn't have enough information to estimate variability in mean letter age. So that's why this green line is constant over time for older ages. What else? For the parametric approach and for the model that incorporated the environmental covariates, we are going to see a temporal trend which is very clear, which is this red and blue line. And this is mainly driven by changes in younger ages. We are still exploring these results. It's very important to say this. But in my opinion, this variability that we observe for all the ages here for these 2 models is driven by changes or by information that we observe in younger ages here. And also, the last thing that we maybe have to say here is that the temporal trend is very similar for all models. I mean, maybe the scale is not very similar, for example, especially for older ages, but the temporal trend is similar. I mean, all the models are following this a similar temporal trend. Okay, this was the first example about the growth variability with these new features that we have. Maybe the main takeaway from this example is that the model is doing good. I mean, the model is replicating the temporal variability that we have in the operating model. And also, we observe that the no-parametric approach needs a good source of data to predict variability in mean adaptation. Okay, in this example too, we simulated data we simulated catch for one fishery, catches for one fishery, index of abundance only for one survey. We simulated land compositions used for the fishery, and also conditional Asian land information for the survey. And also, we had a selectivity at land, which had a double normal shape, and this was for the fishery, if I am correct. I don't remember this, but we simulated selectivity at length, which a double normal function. Okay, just to give you a very quick summary of the results. What we see here are the residuals that we have for the conditional Asian land information, and what we observe here is that there is no weird pattern here. This is a classic plot that we can get from WAM. So what we observe here are the residuals from the observed data and the predicted data. And we don't observe a weird pattern here, so we felt happy or confident about these results. And also, we observe here that the predicted or the estimated selectivity by the model. So yes, this first figure is for the fishery, and the figure at the bottom is for the survey. So for the survey has a logistic function and is a selectivity at length, and for the survey for the fishery it has a double normal function. That's why we have zeros here and zeros for larger sizes. And the parameter for these selectivity functions were estimated. So the model is doing pretty good when estimate these selectivity parameters. And those selectivity parameters were very similar to the operating model. So the model is estimating good. Is doing a good job estimating these selectivity parameters. Cool. So that was about example 2, and now the last example. And for this last example, we simulated data for one fishery, which we have catches, we have an index of abundance, we have land composition for the fishery and for the survey, and we have empirical weather data. Actually, this shouldn't be called empirical. This should be called observed. I need to change this. This is observed weather data, which is going to be fed in the model. And also, we simulated temporal variability in the omega-1 parameter. This is the A parameter of the length-weight relationship. And yeah, with that simulated data, we implemented the WAM model. And what we did was to predict random effects on the omega-1 parameter in the WAM model. And these random effects had a temporal autocorrelation. And we have what we have here is that variability in the omega-1 parameter in the operating model in stock synthesis, and the variability predicted by the WAM model, which is the blue line. And what we can see here is that only using the observed mean weather days information, the model is doing pretty good at replicating this temporal variability in this parameter. So also the model again is doing a pretty good job here. Maybe the model is not good. It's not doing a good job at predicting these like peaks that we have in some years, and maybe that's because the random effects had some kind of temporal autocorrelation. Maybe if we use a different structure, we could have had better results here. But actually, we didn't want to evaluate different options. We only wanted to make sure that the model is working and the model is doing good results or results that make sense with the operating model. So that was our only goal with these three examples. Okay, cool. I will wait 5-10 seconds here. This was just example, as I said, just to make sure that the model is working, that the model is giving reasonable results. And now what we did was to apply those options to a real case study, and that's what I will start talking about in a few seconds. So are there questions about these examples, or can I continue?
You can continue for now.
Cool. Okay. So with these new features, what we did now was to the next thing that we did was to implement a model for the wildlife pollock in the Gulf of Alaska in Guam with these new features. So just to give you a very quick overview of the pollock model in the Gulf of Alaska, this model, the data that we have for this model, we have only one fishery and 6 surveys. We have 52 years of data. We have age composition for the fishery and surveys, and we have mean weathered age information for the fishery and surveys. Regarding the parameters, we have a time varying fishery age selectivity. Some catchability parameters vary over time, and we have, of course, recruitment variability. And all of these parameters uses the penalized maximum likelihood method for estimation. So with that model, the official model is implemented in ADMB. It's a model in ADMB. So what we did was to move the model to take all the information in ADMB and to implement the model in Guam. Oh, actually, this plot is not updated. Well, anyways. And with that information, we got the best possible model in Guam, as similar as possible to the ADMB model. And we got a model similar to this. Actually, this is not the best model, not that I am seeing this figure. Actually, the best model that we got is more similar than to the ADMB model. But anyways, this is not going to change the results that I will present in a few minutes. So this is the best model that we got. And yeah, we can see the temporal trends are very, very similar between these two models. And also this difference in scale for some years is because in this plot or in this figure, catchability prior is not activated. When the prior is activated in Guam, we are going to see that this difference is going to be much smaller. So the model is going to be very, very close to the official model. Sorry about that. I didn't replace this figure for this presentation. But the takeaway again here is that the one model is very similar to the official model that is implemented in ADMB. And in this case, the one model is using the empirical weathered age information to model changes in growth over time. This is because this was the only option available in Guam before this project. Okay, cool. And also that was because the ADMB model uses empirical weathered age information to model changes in growth. Okay, cool. So this was our starting model. This was the best model that we had. Then, using that starting model, we started to implement different strategies to model growth in Guam. And now we selected the wildlife pollock in the Gulf of Alaska because it's a quite interesting case study. We observed the survey data. This is the survey data, and what we observe here in the y-axis is the length. The x-axis is time, and each panel is a different age. And what we observe, each point is a different observation. And what we observe here is that for most ages, I would say like for all of them, we are going to observe an increase in mean lead age from, let's say, like 1990 up to 2010, 2015, more or less, and then there's going to be a sudden decrease in mean lead age for the last years. And that pattern is observed for most ages, as you can see here. So there is a growth variability for this. There is growth variability for this stock, and that's why we selected this stock for a first case study. Now, we implemented the next strategies to model growth internally in WAM. First, to model changes in mean lead age, we use a growth equation, a parametric approach, let's say, the von Bertalanffy equation. And we model changes, or we predict the random effects, which were independent by year or by cohort on the growth coefficient at the asymptotic length. Then we also implemented a no-parametric approach to model changes in mean lead age, and these random effects were independent and varied by year and by age. To model changes in mean weighted age, we used the changes in mean lead age and also a length-weight relationship, which was fixed. We used the classic approach that is using empirical weighted age data. And also we predicted random effects on mean weighted age, and these random effects were independent by year and by age. And the only informative data, informative for growth, the only informative data that we used was observed mean weighted age information. This is the same as the empirical weighted age information, but in this case, it's called observed mean weighted age information because it's going to be fitted in the model. So there is no length information here. There is no conditional age and length data. The only information that we have here is that mean weighted age. So, okay, yeah, we implemented those strategies. And this is a quick summary of what we got here from all those strategies. We have 5 models in total. The green model is using the empirical weighted age. This is the classic approach. The blue model is using the no parametric approach to model changes in mean weighted age, in mean length age. These 2 models, the orange and the black model, are the parametric approaches, but they implement different, the random effects are by cohort or by year. You can see here, this C here represents by cohort and this Y represents by year. And the last model, the sky blue model, is that predicting random effects on mean weighted age. And those random effects are independent by year and by age. This vertical line here is the year when we start to get observed mean weighted age information. And this is the spawning biomass, of course. And yeah, I think we have all the information that we need. Okay, generally what we can observe here is that, especially after 1995 or around 2000, all the models have the same, very similar results. It's a very similar trends and very similar scale. We have a big difference here before 1990. And this is because the empirical weighted age is using average mean weighted age information for early years. However, these 4 models, these last 4 models are using an average as well, but that average is a little bit larger compared to the empirical weighted age. I think that explains this different scale that we observe for the early period. Actually, we don't have options here because we don't have data. We don't know exactly what was the mean weighted age for the population. So it's something that we don't know how to deal with. However, the most interesting things happens after 1995 or 2000, which is when we start to get more data. This is the CV for the spawning biomass estimates. This is the CV, yeah, the CVs. And what we observe here is that the non-parametric approaches got a lower CV. compared to the parametric approaches, compared to the models that use a Von-Bertalanffy function to model changes in mean elevation. So that's the main takeaway from this plot. And this is the plot that's showing the temporal variability in growth parameters. Since these are growth parameters, I am showing only for 2 models, since only 2 models implemented the parametric approach. This is by cohort and this is by year. And we have 2 parameters, the growth coefficient and the asymptotic length. And as we can observe here, different models, we have different conclusions from these 2 different models. When I say this, I am referring to, for example, for the model that implemented random effects by year, the asymptotic length is the main parameter that is explaining that increase in mean layered age over time, and then after 2010, the sudden decrease in mean layered age. However, for the model that implemented random effects by cohort, maybe the main parameter that is explaining that is the growth coefficient here, especially after 2000. And then the asymptotic length, of course, had a negative correlation with this parameter. So we got different conclusions using these 2 different approaches. Now, what I am showing here are the fits of the results of the predicted mean length and age information from these models. And also we have the data. This is the data from the survey. Just to remember, this data is not included in the model. So this is data, the model is not using this data. And what we can observe here is that the model is predicted a temporal variability very similar that as we observe in the data. These are we only have 3 models here because only these 3 models model changes in mean length age. And yeah, and we can see here the temporal variability is very, very similar for all ages. And finally, we did a very quick model comparison. We are showing here the AIC values for models with the same input data. The main takeaway here is that the no parametric approach, which is the first model, is the model that got the best results. I didn't show the fits of the observed mean weathered age, but if we compare the fits of that data among models, we are going to observe that this no parametric approach had a smaller residuals and therefore a better performance. Okay, I have some final thoughts here. This is the last part of my presentation. What I presented here is a new tool to explore growth modeling in static space assessment models. The no parametric approach that I presented here seems to outperform a classic parametric equation, a classic parametric equation. And this is quite interesting because this no parametric approach is more flexible than parametric equations. We don't have to care about what is the initial value for the growth rate or for the asymptotic length, and we only have to start with mean layered age values for the population, and the model is going to predict the random effects on that. So it's going to be it's going to have normally well, for this case, it had a better performance compared to the parametric approaches. But also, as I presented in my examples, we need good information to predict those random effects. So that's going to be very important to consider. And as I say, this no parametric approach is more flexible and deals with fish shrinkage. As we know, the parametric approaches doesn't allow to fish to decrease in size when the fish gets older. However, this parametric approach can do that if the data is telling me that. Now, some future directions that we are taking for this project is that we are going to include surveillance information, for example, marginal length compositions, conditional HLN data, just to inform the model about the growth variability as well. We are exploring environmental covariates to include in the model and to model changes in growth. And we are going to perform, of course, simulation experiment just to get more general conclusions about the best strategies to account for growth variability in Guam. Perhaps from this last point, we are going to get good practices for growth modeling in static space models. And also some future directions in general is that when I say this, like future projects can work on, is about software development. As I said, this WAM is a quite new platform, so there are more things that needs to be implemented to be applicable to other stocks worldwide. For example, we can include sex structure, intra-annual variability. We can include staging data, some kind of spatial structure. A question that I have in my mind now is about the performance of different platforms to deal with growth variability. For example, what's the performance of the stock synthesis compared to WAM to model growth variability, and do some kind of ecological research about what is the meaning of all the random effects options that we have. In what cases we should use one structure, in what case we should use a different structure, in what case we should use a temporal autocorrelation. All those options that we have, and try to think about some ecological meaning of that. And this is my last slide. Thank you for listening. I acknowledge my co-authors here, Tim Miller, which is the main developer of WAM, and as well with Brian Stock and Jim Janelli for his comments. I acknowledge my sponsors, and if you want to know more about the work that we are doing with WAM, you can visit this website. This is my contact information. If you have more information, or you want to know more information about this project, and also if you are interested in applying these new features to the stock that you are working with. Actually, we are looking for case studies. We only have one case study so far, but we would like to apply these new features to more stocks, just to understand more the performance of all these new options that we have. And yeah, I will be happy to take questions if there is still time.
Thank you. That was a great talk. I have a question from Cole Monahan. Does anyone have any thoughts on the validity of using AIC to compare the mean weight at age and length at age, non-parametric versions of the model?
As far as I understand it, they are using the same data input. I mean, the same source of information that can be compared. So the only thing that is going to change internally are going to be the random effects estimated for mean letter age or mean weather age. I don't know if I got the question right.
Cole, if you have anything to add, I can unmute you. He says, it's very surprising to me that the length at age would be so much better. So he's kind of skeptical.
Length at age is much better than weather age.
Mm-hmm.
Yeah. Yeah, I don't know what to say about that. Actually, that a simulation experiment will respond that question. We have only tried those two approaches with these case studies, so I think a simulation experiment will be the best thing to answer that. Yeah, and actually, they are not quite different. They are not very different, I would say. The performance and the residuals that I found for both models are quite similar. So yeah, but the mean weather age approach was a little bit better compared to the mean weather age approach.
I had a question. I was curious for the one when you tested the year random effects versus cohort random effects on the parameterized versions of the length at age. I was curious if you had an insight to why you thought they switched what was influencing the parameters more, and if that's something that you would expect kind of across the board for different species, or more of just a Pollock thing.
That, again, I don't know. Actually, I am still learning about the ecology of this species. There is evidence that for different stocks, the cohort effect is more important than the year effect. But for other stocks, the year effect is more important than cohort effect. And there is also an age effect in some stocks. So there's many things playing together here. In this case, we only have the option to separate cohort effects and year effects. In the future, hopefully, we can implement some kind of a 2D autocorrelation between cohort and years and ages. For the Pollock example or case study, there is no ecological reason why I try the cohort effect or the year effect. Actually, that's something that we are exploring now because we don't know exactly what's more important. So here for my presentation, I only let the model tell me what is the best for the model. But actually, I don't have ecological reason to try one or a different one, to try one or the other one.
It's interesting. Thank you. Cole has another question, I guess, to you, Giancarlo, and also the group. If anyone has any experience fitting weight at age inside a model, what observation error did you use?
Yeah, we calculated the observation error from the data. I mean, when I say this, I am not estimating observation error parameter in the model. What we did was to take all the observed data, calculate a CB, an error for each age and for each year, and that error calculated from the data was included in the model, and that's the way how we dealt with the error structure in the Pollock model. However, there are options to estimate a parameter. I mean, just to let the model estimate a observation error parameter when we have length composition or when we have age composition. So we have those options, but we haven't tried those options yet. I don't know, Cole, maybe you want to complement this.
Cole, if you have anything else to say, you can unmute yourself. I have another question. So you mentioned a few times that WAM's a new platform. Besides the growth stuff, like what would be like the next on your wish list for additions into the software?
Yeah, great question. First, I think the first in the list is sex structure. There are many stocks here in Alaska. Well, not here in Alaska. that needs that feature to implement a model in WAM. So sex structure is something that probably soon that some people are gonna be starting to work on. And then there are many options. I mean, taking data intra-annual variability could be the next two steps, and the last step could be some kind of spatial structure, which is gonna be more complicated. So that would be my opinion. I mean, as I said, there are many things to do here. WAM is not as flexible as other platforms, for example. So the flexibility of WAM could be another thing to work on. but as I say, this one started to be developed just a few years ago. I think the first paper on one was in 2016. As far as I know, I don't know if people know more about this. So it has been only 5-6 years. So there is still many things to work on here, and it's promising. I mean, the results that we are getting so far are very promising, and they can be applied to many stocks already.
Awesome. If anybody else has any questions, you can drop them in the chat for the questions box.
Or comments. I wanna learn too,
yeah.
and I wanna get some feedback too. Yeah, especially about case studies. Anyone here in the audience know about a case study that we can apply these new features to?
I have a comment from Sabrina Bayer. She says, very nice talk. In the pollock case study, the spawning stock biomass through time seems slightly biased higher for the new methods compared to the base model. Any insights as to why or any concerns about that?
Yeah, but let me show that plot again. It's this one. Actually, I will be honest about this. The empirical validation information is something that we already have in the ADMB model, which is the official model, but I personally don't know how it has been calculated. That's something maybe that Cole can answer. So the first thing that I want to make sure is about if there is a kind of estimation, different way that we are calculated that empirical validation matrix. And then the other approaches that we are having here are starting non-parametric approaches, for example, are starting with mean validation, mean validation obtained from the entire time series. So maybe that's something that we need to consider here, because that's something that it can overestimate the spawning biomass here. That's my guess here. But actually, I just want to make sure first how that empirical validation information in this green model is being calculated to be incorporated, which is going to be very important. And again, that's why we want to do a simulation experiment here. But a simulation experiment is really going to deal with which is the best approach to account for growth variability in the model. It's going to be the only way to do that. And that's something that we are going to do within the next weeks. So hopefully soon we are going to have a better answer for that.
She says, sounds good. Thank you.
Thank you for the question.
Okay, so I have a question from Matthew Vernon. Great talk, thank you. I was wondering if you thought to incorporate random effects, environmental effects on the initial length at age for the parameterized version. I think that a lot can happen at the beginning of the life cycle and drive the maturation schedules, the overall growth patterns, as well as mortality patterns.
Yeah, I totally agree. Those are questions I have in my mind. I have worked on changes in growth during the early life stages for the PICOT in the EBS, and that period is very important with it because it's going to change a lot the mean at age 1, and that's going to drive changes in the mean length for all the ages. So I think that changes in mean at age 1 is going to be important to work on in the future. But actually, as I said, it's not very clear to me yet what is the ecological driver of these changes in mean age over time. It changes in mean age 1, it changes in the K parameter, it changes in asymptotic length, because those changes are driven by different parts of the environment. And each component has a different meaning of the population. So I think there is still a ecological research that should be done before we deal with those hypotheses in the stochastic model. again, I think that that's the best answer that I have so far. So it's something that we are still exploring. Hopefully, we can have an ecological answer, a better ecological answer soon.
Matthew says, okay, thanks. We can talk later about this.
Thanks, Matthew.
Mhm. I think that's all the questions I see coming into the chat or question box at the moment. I think we can either wait another minute or we could wrap up. Anyway,
No. Yeah. Again, anyone in the audience know about a case study to apply these new features? Any case study that you maybe have in mind? Yeah, if not, again, you can contact me and we can chat more about that.
Oh, Aaron Berger suggests Pacific hake would be an interesting case study.
That would be nice, but as far as I know, there is a special structure in that model. So if it is a single area model, that would be great.
It is a single area, Aaron says.
Oh, cool. Okay, great.
Awesome. Well, thank you, Giancarlo. This was a really cool talk. Didn't know much about WAM coming into this. Yeah, and then everybody else, thank you for coming today. Giancarlo has his contact information here, and then we'll have the recording for this think tank up in a few days.
Okay, thank you, Emily, for the invitation, and thank you, everyone, for listening. See you soon.